In this video, I'm going to show you how to solve optimization problems involving boxes and trays. So here's our first problem. Suppose we want to build a box that has a square base and no lid. If we have only 12 square centimeters of sheet metal, what is the largest possible volume of our box? Here we've got a diagram of our box. It has a square base, so both of the sides of the base have the same length, and then there's also the height. Okay, so let's jump into the problem. What is it that we want to optimize? We want to optimize the volume, so let's write down the volume formula. Volume is equal to the base area, which in this case would be x squared, times the height, h. But in order to optimize this function, we need to get it down to a function of a single variable. So that means we need to find an equation relating x and h together and solve for one of them in terms of the other, so we can sub it back into this volume formula. So when we're thinking of our next equation, we should think about what other information we're given in the problem. In particular, we're told we have only 12 square centimeters of sheet metal. So that's a constraint on the surface area on the box. So we have that surface area equals 12. And we can express our surface area in terms of x and h. First of all, there's the base of the box, x times x squared is the area, and the box has no lid, so just a single x squared. And then there are 4 lateral sides on the box, a front, a right side, a back side, and a left side. So plus 4 times the area of each lateral side, which is x times h. So plus 4x h equals 12. And in this equation, it's going to be easiest to solve for h, because h only appears once in the equation. So let's go ahead and do that. So we'll subtract that x squared over to the other side, get 4xh equals 12 minus x squared, and then divide by 4x to get h equals 12 minus x squared over 4x. And that's what we can put into our volume formula. Volume equals x squared times our expression for h in terms of x, 12 minus x squared over 4x. And we can go ahead and simplify this, just multiply it through. This becomes 12x squared minus x to the fourth over 4x. And now 12 over 4 is 3. X squared over x is x. And then minus 1/4. Then x to the fourth over x is x cubed. So that's our volume function as a function of x. Okay, so now we've got our function of a single variable, and now it's time to optimize that function. And the way we optimize the function is we take its derivative, v prime of x, and we set it equal to 0. We're trying to find the stationary points, because those are candidates for the maxima or minima of the function. So taking the derivative of 3x is just 3, and then minus power rule on that 1/4 x to the third, the 3 jumps out, 3/4, and then the power decreases by 1, so x squared. That's equal to 0, which means we can just solve for x squared here. How about add 3/4 x squared to both sides? You get 3 equals 3/4 x squared. Multiply both sides by 4/3 to get that 4 is equal to x squared. And now we'll take the root, and since x is a physical length, we want the positive root, so 2 equals x. So that's our critical point. We'll circle it, but that's not our full answer yet. We want to find the largest volume of the box. And before we do that, let's just verify that this critical point is indeed a maximum of our volume function. We can do that with the second derivative test. Take the derivative again, the second derivative. That's equal to, well, 3 goes down to 0 because that's a constant, and then applying the power rule to negative 3/4 x squared makes negative 3/4 times 2x, which simplifies to negative 3/2 x. So that means at our critical point of 2, the second derivative, evaluated at 2, is negative 3/2 times 2, which is negative 3, which is less than 0. So that means the function is concave down, and our critical point is at the top of a parabola-looking part of the function, which means yes, x equals 2 is indeed a maximum. Okay, so now all that remains to do is to sub in that x equals 2 into our volume function, and that'll give us our final answer. So volume function evaluated at x equals 2 is 3 times 2 minus 1/4 times 2 cubed. 3 times 2 is 6, and then 2 cubed is 8, then 1/4 of that is 2. 6 minus 2, that is equal to 4. And let's put our units on. This is units of length cubed, and length is centimeters, so centimeters cubed. That is the largest possible volume of our box, 4 centimeters cubed. Alright, on to the next problem. Consider all the fully enclosed boxes that have a square base and volume of 27 centimeters cubed. What are the dimensions of the box with the smallest surface area? Okay, so again we've got our diagram here, and first thing, as usual, let's write down the expression for what we want to optimize. We want to minimize the surface area, so let's write down the expression for surface area. Surface area is equal to what? Well, that's just the area of all the faces, and this box is fully enclosed, so it has both a base and a top of area x squared, so there's 2x squared, and then there's 4 lateral faces of area xh, so plus 4xh. Now, in order to optimize the surface area, S, we need to write S in terms of a single variable. And to do that, we'll need an equation relating x and h. So let's see, what other information are we given in the problem? Well, we're told that the volume is 27 centimeters cubed. So volume equals 27. And we can express volume in terms of x and h. Volume is just the base area, x squared, times the height, h. So x squared h is equal to 27. So we can solve for one of these variables in terms of the other. Why don't we just solve for h, because that doesn't have any exponent, and that'll yield the simplest solution. So h equals 27 over x squared, and we'll plug that back into our surface area function. So surface area is equal to 2x squared plus 4x times our expression for h in terms of x, which is 27 over x squared. And we can simplify this a bit. This is just 2x squared plus 4 times 27 is 108, and then x over x squared makes over x. So there is our surface area as a function of x. Now we want to optimize this function, which means we want to find the stationary points. So set s prime, the derivative, equal to 0 and solve. So differentiating 2x squared, apply the power rule, 2 times 2x makes 4x. And then 108 over x is like 108 times x to the power of negative 1. Bring down that power of negative 1, so negative 1 times 108. Then decrease that exponent by 1, so x to the negative 2, which means over x squared. So that has to be equal to 0. Now, since x is a physical length in our problem, we know it's non-zero. So that means there's nothing wrong with multiplying our equation by x. So why don't we multiply both sides of the equation by x squared to cancel out that denominator? We'll get 4x cubed minus 108 is equal to 0. And then we can solve for x. So 4x cubed is equal to 108. Divide by 4, get x cubed is equal to 27. And then take the cube root, x is equal to 3. And you can check the second derivative to verify on your own that this is indeed a minimum of the surface area function. I assure you it will work out. So this is one dimension of the box with the small surface area, but we still need to find the height, and that's simple now that we know what x is because we had a formula for h in terms of x. So h is equal to 27 over x squared, and x is 3. So 27 over 3 squared, which is equal to 27 over 9, which is equal to 3. So h also equals 3. So that means the dimensions of the box are x by h, which means 3 by 3 by 3. And why don't we put the units on as well? These are units of length. So 3 centimeters by 3 centimeters by 3 centimeters. Final answer, 3 centimeters by 3 centimeters by 3 centimeters. Those are the dimensions that will minimize the surface area. And this makes sense intuitively because the box is perfectly symmetric. It's a cube. So now we know how to solve optimization problems involving boxes and trays. And in the future, we'll also learn how to solve optimization problems involving other shapes, like cylinders, and shapes inscribed in circles.